This screencast is on acid-base equilibrium calculations involving polyprotic acids. Now remember, a polyprotic acid is an acid that contains more than one acidic hydrogen. Remember, these acids dissociate stepwise, so one hydrogen at a time. So for a typical polyprotic acid, what will be true is your Ka1, the equilibrium constant from the first dissociation step, is always your greatest. The Ka2 and then Ka3, they successively get weaker and weaker. Now, with a polyprotic acid, only the first dissociation step is important in determining the pH because it's the only one that contributes to any degree to your hydrogen ion concentration. It's just like with our mixture of weak acids. Remember, we use our strongest acid present to determine the pH. So that's the one with the greatest Ka. So with the polyprotic acids, the first dissociation step, the first Ka value, is the greatest. The calculation is identical for those of weak acid calculations. Now, sulfuric acid is unique because it is the only strong acid that happens to be polyprotic. So if the concentration of the sulfuric acid is greater than or equal to 1 molar, the large hydrogen ion concentration from that first step greatly represses the second dissociation step. So we can completely ignore the second dissociation step as long as the concentration of the sulfuric acid is greater than or equal to 1 molar. Now, if you have very weakly or a very low concentration of sulfuric acid, even though it's a strong acid, if it's less than 1 molar, the second step is significant. So you would need to use the quadratic equation to help you solve, and it would be solved more like the polyprotic acids that we will look at. We're going to look at a couple examples in our examples. So I'm going to switch over to the problems that we've been using in class. So I'm going to come on down to problem number 7, and this is the guided and practice problems worksheet that we've been using in class. All right, so this question number 7 says, calculate the pH of a 5 molar phosphoric acid solution, and it wants you to calculate the equilibrium concentrations of the phosphoric acid, the dihydrogen phosphate ion, the hydrogen phosphate ion, and the phosphate ion. Let's first determine the pH. Now, polyprotic acids, if you look in your book, you'll find the Ka values for each of these 3 dissociation steps. But remember, the first dissociation step is the only one that contributes really to the pH. So that's the one we're going to be using. So we're going to dissociate H3PO4. Since it's a weak acid, you're going to pull off 1 hydrogen, and that's going to pull apart and leave behind H2PO4 negative. And in the appendix of your book is where you'll find these Ka values if they're not given in the problem. Let me just kind of talk to you about the K values. So the Ka1 is the one we're talking about here for this one, is equal to 7.5 times 10 to the negative 3. For the second dissociation step, that's Ka2, it's 6.2 times 10 to the negative 8. And for the third dissociation step, Ka3 is 4.8 times 10 to the negative 13. Now, another K that we always need to be aware of in solution, because these are aqueous solutions, is the Kw, the ion product constant for water, which is 1.0 times 10 to the negative 14. So if you look at all the K values, the equilibrium constants, the one that controls the pH is the greatest one, which is your first dissociation step, which is the one we're going to use here because it is the Ka value for the phosphoric acid. So let's ice our problem, get our information in here. That we were told the concentration initially of the phosphoric acid is 5.0 molar. So that goes here in the initial, and we have 0 ions initially. We define our shift in terms of x, so minus x, and plus x. Remember, if we have an initial amount present, we can neglect our x. So we're going to neglect the x here because this is a weak acid. You can do this neglecting x with weak acids or weak bases class. So 5.0 molar at equilibrium, and x. So now we're ready to use our law of mass action. So Ka1 for this is going to be equal to concentration of hydrogen ion times concentration of H2PO4 negative over the concentration of H3PO4. So let's substitute in our numbers. 7.5 times 10 to the negative 3 equals, both of these are x, so we can condense that as x squared over 5.0. Again, since we're neglecting x, this is an approximation. Always remember to double check your 5% rule at the end, but this one is well below 5% whenever you check it. So we're going to cross multiply here and then take the square root to get our x. And so that's going to give us a total of 0.19 molar as our answer for x. So let's look and see what exactly we've solved for here so far. So we just solved for x, and x happens to equal the hydrogen ion concentration and the H2PO4 concentration. All right, so keep that in mind. Now, some things that they wanted us to figure out in this problem were the pH. So we're going to find our pH. They wanted us to find the equilibrium concentrations of H3PO4. So we know that's right here is 5.0. If we wanted to be specific, we could come back in and substitute in the value for 0.19. So you could, if you come back and substitute in, you get 5.0 minus the x value, because notice here it's 5 minus x, so you could say minus 0.19. So technically that would give you 4.8 molar. For the hydrogen ion concentration, we have 0.19, and that's also equal to the H2PO4 minus ion. So they're both 0.19 molar, and those were two things they wanted, that and that. And the pH, let's go ahead and find that because this is our hydrogen ion concentration. So the pH is equal to the negative log of hydrogen, and in this case, negative log of 0.19. So for your pH of this solution, we need 2 decimal places because we have 2 sig figs. The pH is equal to 0.72. So now we have our pH. Okay. So we found the pH, we found the phosphoric acid, the dihydrogen phosphate ion concentration. And so now we're going to continue on, and they want us to find HPO4 minus 2 and PO4 minus 3 concentration. So what we're going to do that, we're going to ice the problem. We're going to look at our dissociation that occurs with the HPO4 minus 2. All right, so to find HPO4 minus 2, we're going to look at that dissociation. So let's take the second dissociation step, H2PO4 minus, and let's dissociate that. H plus HPO4 minus 2. And we're going to ice that problem. So we're going to plug this in here, 0.19. I will pick up with this problem on the next video.